All right, so now we're going to continue with chapter 5, and right now we're going to focus more on exponential functions. Before we were focused mainly on logarithms. Now we'll be looking mainly at exponential functions, but we'll be looking at them both throughout the rest of the chapter. All right, so first things first, why don't we remind ourselves what E is? E is a constant, and if you go to your calculator, you'll see it's right there. You can find the value of E by taking E and raising it to the first power. And you look in the screen, you'll see that this is approximately what it's equal to. But you'll see in the next slide how one way we can formally define it. So, and then later on, we're going to see another way, but that has to wait till the end. So right now, though, it's important to note that the log of x and e to the x are inverse functions. Okay, so the natural log of e is 1 because remember that ln simply stands for log base e. So therefore, the log of base e of e has to be 1 because e to the first power equals e. So remember, if in the previous section, we defined logs in terms of an integral. Well, something like that is happening here. We're taking the same function y equals 1 over t, and we're integrating over the range from 1 to x. Actually, we're defining here log x. This is what we defined in the beginning. Log x equals the integral from 1 to x of 1 over t dt. But if we replace the x with an e, you can see that log e ends up with an integral of 1. In fact, if you wanted to prove that, what you could do is, let's see, hold on. Let me show you a little proof here. All right, so in other words, if you have an integral from 1 to e, this is a definite integral because we're applying this over a specific range of values from, in this case, 1 to e, 1 over t dt. And if you recall that this is nothing but the log of t, although it's actually the log of absolute value of t, we don't need the constant c because this is a definite integral, and we evaluate this over the range from 1 to e. Okay, so we end up with log absolute e minus log absolute 1. We don't need the absolute values here because these are clearly positive values. And if you recall, the log, no matter what the base is, of 1 equals 0, since b to the 0 equals 1. So that means we have log e minus 0. But of course, log e itself, as we just showed, is 1 since e to the first power equals e. So you just end up with e minus 0 equals e. Okay, so that's our proof that the area under this curve from 1 to e is 1. Okay, so now the graph, if you recall, if we've seen this before, y equals e to the x looks like this. Now, if you notice, it grows very quickly because this is, after all, an exponential function. Whenever we have x as our in our exponent, that becomes what we call an exponential function. The book sometimes to distinguish this from other exponential functions, like, for example, y equals 2 to the x, the books will refer to this one as the log exponential function or something along those lines, just to make it clear that we're talking about e to the x. Now, if you notice, it crosses the vertical axis at the point 1 comma 0, because when x equals 0, we end up with 1. And then after that, it just goes through the roof. Basically, it grows very, very quickly. We sometimes see exponential functions used to describe the growth of an investment, let's say, or it may be, you may have remembered from high school biology, you may have studied how bacteria multiply very quickly. The growth rate of the bacteria may be described with an exponential function because it happens so quickly. So this is our e to the x function. And just a quick reminder, e to the x and log x are inverses of each other. So because of that, and you could prove that if you want to remember with this technique we have. In fact, what the heck? We have a few minutes here. Why don't we prove this? It's good practice. All right. So in other words, let's say that f of x is log x. G of x is e to the x. Okay. So because these are, we claim that they're inverses of each other. So we can prove it by showing that these two conditions must hold. So let's start with the first one, f of g of x. You're taking f, the function f, and replacing all the x's with g of x. You make the substitution. All right, so we know that this is going to equal x because, again, this is the natural log base e. And then we have to do the opposite. So g of x is e to the x. We replace that x with f of x. And based on the properties of logarithms, this is also equal to x. All right, so there we are, our proof that these two are inverses of each other. Sometimes you can tell by looking at a graph. Sometimes it's not so straightforward, but just as a rough idea, okay, well, it's not perfect, but you can kind of see what it's going to look like. It's almost like there's a mirror here, and they should be mirror images of each other. All right, anyway, so as we just saw, log e to the x equals x, e to the log x equals x. We just demonstrated y. So now here's the beauty of this. Those logarithmic properties, like I said earlier, can really help us simplify a very complicated problem. So here's a good example of this. Imagine you're confronted with this equation, 7 equals e to the x plus 1, and of course you're trying to solve for x. What do you do now? Well, why don't we try this? Let's take the log of both sides, the natural log, that is. And you'll see the advantage of doing this is that you have the log of e to some power. Let's call it g of x. It's simply g of x. So that means that the right-hand side reduces very nicely to x plus 1. The left-hand side is the log of 7, which is a constant. So we subtract 1 from both sides, and this is our final result. Oh, now that wasn't so bad. Okay, so in other words, once we recognize that we can simplify using the properties of logarithms, if e is the base, then we'll use natural logs. If we had something different, like 7 equals 3 to the x plus 1, you would then want to use the log base 3. Okay. Otherwise, you're just making a bigger mess. All right, so let's try another one of these. Suppose we start with a logarithmic equation. Now look what we can do. So keep in mind, e to the log of g of x is simply g of x. So look what we can do. And then, of course, this reduces to 2x minus 3. Well, now we're all set. E to the 5 is simply a constant. And we're done. Oh, look how much easier that was. So, of course, we're taking this exponential function and applying it to both sides. We're allowed to do that without changing the results, and we're done. Nice. All right. Anyway, here's a quick review of how exponents work with exponential functions. E to the p times e to the q equals e to the p plus q. Then similarly, e to the p over p to the q is equal to e to the p minus q. And then finally, e to the p, and then here the entire expression is raised to the r power. That leaves us with e to the pr power. So by the way, these properties work no matter what the base is. In other words, it would work for 2 or 7 or whatever. This is not unique to E. The domain of f, and just by looking at the function, you can see the domain is all real numbers. There is no value that would cause a discontinuity here or an imaginary number. But at the same time, though, the range, you can see that the horizontal axis is acting as an asymptote. So the function will never actually hit 0. Okay, so 0 represents our asymptote, and therefore the range is everything from 0 up to infinity, not including the 0. Right. And if you go back and look at the first part, you'll see this is the same for log x. Now, how do we take derivatives of exponential functions? Well, the derivative of e to the x equals e to the x. That's simple. But what about e to the g of x? By the chain rule, we have a separate case for that. That means that we end up with e to the x times g prime of x. So it's a very simple derivative to calculate. I mean, unless g to the g of x is a nightmarishly complicated function. So let's look at some examples. So here we have e to the 4x squared minus x plus 1. So of course we'll assign g of x will become 4x squared plus minus x plus 1. And then based on the power rule, g prime of x is simply 8x minus 1. So you can see how straightforward this is when you substitute. You just end up with the original function, e to the 4x squared minus x plus 1 times g prime of x, which is 8x minus 1. Okay, and you can leave it like that. You don't, I mean, you could simplify, you could multiply, but there's no point. You can just leave it like this. All right. Oh, look at this one. Now you might look at it and say, what do we do now? Should we apply the product rule? And the answer is we could, but there's no need because if you recall from just a minute ago, all we have to do is rewrite it. It would be this case as and now we can use the chain rule that we just saw. So yes, if you wanted to, you could have used the product rule, but why bother? You know, the thing is you should really always use the most simple approach you can because it saves you time, but it also reduces the risk of making mistakes. So now we're all set because all we have to do, remember, here's our chain rule for e to the x, or e to the g of x, I should say. And so we have g of x is that exponent, 3x plus x squared. G prime of x, based on the power rule, which we always use with polynomials, is 3 plus 2x. So we end up with the original function, e to the 3x plus x squared times g prime of x, which is right here. All right. Now, what about integration? Okay, well, if the derivative of e to the x is just e to the x, it stands to reason that the integral of e to the x is e to the x, but we don't want to forget about our c if we're trying to calculate an indefinite integral. If we have u, remember u is a function of x, then we'll have e to the u plus c. But remember, this requires us to have the proper du under the integral sign. And that's usually the challenging part, making sure that if you think it's in this form, that you have the proper du here. And sometimes, as you recall, we may have to supply a constant to make sure that that happens. Like here's an example, a perfect example of this. We have the integral of e to the 2x. Okay, so let's just call this our u. And that being the case, du dx is 2, or du is 2 dx. We don't have 2 dx, do we? Not a problem, because this is the same as this. Just multiply by half and 2, so we haven't changed anything. But now suddenly, look what we have. This is our e to the u, and this is a du. So then we can go ahead and integrate. And you can see down here, we just end up with 1/2 e to the u plus the constant. And then we replace the u with its definition of 2x. So we have 1/2 e to the 2x plus c, and we're done. So I think, this chapter, although there's a lot of material here, the techniques themselves are actually very, very straightforward. Okay, we've seen other chapters where that wasn't always true, but here, yes, these are very easy to work with: logarithms, natural logs, and exponentials. Oh, now what's going on here? We have to look at this one very carefully. And there's different u's that we could potentially choose here. And so, like, as is always the case, and by the way, don't forget, choosing a u means you're using the method of substitution. As always, if you choose the wrong u, you'll notice it right away, because you end up with a result that's even messier than what you started out with. Either that, or you don't have the right information to solve the integral. So if you guess wrong, fine, try something else. It's not the end of the world. So here, why don't we try this? And by the way, just as a rule of thumb, when you're doing one of these, you probably should go find wherever the highest exponent is and let that be your u. Because as you know, then the derivative could be whatever's left over. So here, for example, we let u be minus x squared. Du dx is minus 2x. Du is minus 2x dx. So if you notice, we do have our 2x. Guess what we don't have? We don't have the minus. But that's not a problem, because we can supply it ourselves. Okay, what we're effectively doing is supplying a -1. And so in order to do that, of course, we have to multiply the outside by -1 so that we can multiply the inside by -1. Now all of a sudden, we have minus integral e to the u du. And that is very easy to solve. Okay, so minus e to the u, here it is e minus e to the u plus c. And then we replace the u with minus x squared. And here's our result. All right. Now, here's some more results. Now, these are going to help us again with more complex problems. So based on the properties we've been looking at of logarithms and exponential functions, y equals a to the x. Now, if you notice, I'm used to seeing e to the x. What happens if it is not e to the x, but some other constant? This is equivalent to e to the x log a. Okay, now log a is simply a constant. So by writing it like this, you'll find that we can apply the rules that we've just been learning. And of course, if x is instead a function of x, then we end up with this result. Okay, e to the g of x times log a. By the way, a has to be positive for this to work. Now look at some of these others. Now, you look at these and say, wow, these are some complicated looking definitions, but these are very similar to what we've already seen. This is equivalent to log e to the x equals x. If you let a equals e, and the same thing down here, this is the same thing as saying e. If you replace a with e to the log x equals x. So think of this as a more general version of these two rules that we saw earlier. These apply for any a, including e itself. And the same thing could be said for this one. Log e is just 1. So you end up with just log x. Huh, how do you like that? So this one is true for any a, But of course, we know the special rules for when E is the constant. All right, so these rules here are going to help us deal with cases where we have a constant other than E. Okay, so for example, d a to the x equals a to the x log a. Now, if E was equal to a, what this would have turned into is d dx e to the x equals e to the x log e, which is just one. So it's perfectly consistent with what we've been doing. Okay, and the same thing down here. If this had, sorry, had I replaced this a with e, I'd have e to the g of x log e g prime of x. The log e is just one, so we end up with e to the g of x, g prime of x, and that's the chain rule that we know for the exponential function. So this is just a more general version of what we've been doing, where that constant could be anything, as long as it's positive, that is. And so similarly, we have the integral of a to the x is 1 over log a to the x plus c. The derivative of log of other base than e is 1 over x log a. And then finally, the derivative of log a, g of x, is g prime of x over g of x times log a. Now, you might want to think about copying these onto a list somewhere. So when you're doing the assignments, you've got them all together in one convenient location. Either that, or just make a note to yourself that all of these are found here. Now, I don't think the book has a separate table for these. They're probably just, found in whatever chapter you're reading. But unlike the integral formulas, which are all at the end, I think these are just scattered throughout the entire chapter. So you might want to think about looking into some cheat sheets, I guess you could call them. Oh my God, look at this disaster. What are we supposed to do with this one? Well, does it remind you of any of these cases? Let's find out. Well, it turns out this is maybe a bit of a trick question, because look what we can do. This is the challenging part. Actually, no, I'm writing this incorrectly. Sorry. So let's just make an example. Suppose that x is 3. 4 to the third power is 64. 2 to the 2 times 3 is 2 to the 6, which guess what is 64. So this was the interesting part right here. And so we're going to replace this with this. Now, why are we doing this? Because now suddenly we have two numbers that both have the same base. And so I end up with 2 to the 2x plus x squared in my exponent. Okay. So in a way, if you saw this, you'd recognize right away, this is the derivative of a to the g of x. That would be this one. But it was written in such a way that you might not recognize it right away. So the challenge would be to recognize that, we can rearrange this algebraically. And suddenly we are able to use a rule. So here it is. And so in this case, a is 2. And g of x is 2x plus x squared, which means that based on the power rule,
G prime of x is 2 plus 2x. So here we have a, the g of x, log a, and g prime of x. And that's our answer. It might be possible to simplify it a little, but if not, we can just leave it like this. That was pretty scary. Now, of course, there's always multiple ways of getting to the same result. We could have used the product rule, for example, and then but it probably would have taken longer. And then for each one of these, you would be using this formula right here. Okay. Actually, you know what we might want to do is just to double check. Why don't we try that? Okay, just for the fun of it. It's not necessary, but suppose you said, I didn't recognize that. Why don't we try it this way? But remember, for both of these, we can apply the same rule. You've got a to the x to some function of x power, meaning this one. So first things first, you have to apply the product rule. Think of this as f of x and g of x. You're going to have the derivative of f of x times g of x, as you remember, is, oops. All right, so we already know f of g of x, but what is f prime of x? Okay, so f is this one. We're going to have a to the g of x log a. G prime of x will just be 1. Okay, because here the exponent is the g of x. G prime of x, that would be this one, is the original function on 2, and then the derivative of that function is 2x. Wow, this is going to be messy. So when you plug these in, you're going to have 4 to the x and then we're going to have 2 to the x squared, and then we have f prime of x, which is 4 to the x. Wow. So, yeah, that looks kind of messy, but we do have some common factors at least. Okay. And let's see. Let's move this to the next slide. All right, I'll just write it down. Sometimes it lets me copy it, sometimes it doesn't. I don't know what the reason, there's no rhyme or reason to it. All right, so the one thing we do know here is that the log of 4 is the same thing as log of 2 squared, which can in turn be written as
2 log 2. So we can write this as 4 to the x, 2 to the x squared. Okay. So that should be what we had before. Let's confirm that. I'll copy it up here somewhere. Oh, and by the way, don't forget, we determined that this is the same thing as 2 to the 2x plus x squared. So we did it. It was a lot of work. But now when you look at it, you'll say, wait a minute, why did we go through all that? Why did we use the multiplication rule? Well, if you didn't recognize that this could be simplified into a single term, there really aren't any other good options. So you would have gone through all these steps and you would have gotten the same answer. Okay, it's not the end of the world, but you could have saved yourself a little time had you recognized that this could be rewritten as 2 to the 2x, 2 to the x squared. Okay. But it's good to know that it works either way. All right, now this one, okay, here we go. For the first time, we're seeing we have log to some other base of g of x, and that would be this case. See, this is why it's so nice to have a chart. Imagine if you had to go to the book and find this every time. No, we don't want that. So here a is 8. G of x is what's in parentheses 7x squared plus 4. G prime of x by the power rule is 14x. So according to this formula, we're going to have g prime of x is on the numerator. In the denominator, we have the g of x. And here we have the log of a, which is 8. And that's it. I mean, we can't do any more simplification here. 14x over 7x squared log 8, and we're done. So the key here is to recognize which case we're looking at. There wasn't any opportunity here to do any simplification, so we'll just go ahead and use the rule. Oh, now that one looks pretty terrifying. What do we do with that one? So it's a raised to some function of x. Let's see, do we have that one? Why, yes, we do. So I'll sneak this up here.